Hi, folks. We are back. We're going to be talking about a very interesting topic called the bias-variance decomposition, which is a frequentist approach of to looking at the effects of regularization and how to pick the right regularization parameter, um, and how that is determined by the way low and high regularization affects the models that are learned and how those in turn then affect the errors that you're trying to avoid and minimize. Um, so yeah, I think let's just get to it. One thing that's going to be cool about this session is I've actually got wrote some code to kind of try out some of the ideas, reproduce some of the figures in the section. So I will put a link to that afterwards, and I'll go through some of it with you after we talk through the section, so you can actually kind of see how to compute these concepts yourself. Okay, so now it says, so far in our discussion of linear models for regression, we have assumed that the form and number of basis functions are both fixed. And then as we have seen in chapter 1, the use of maximum likelihood or equivalent least squares can lead to severe overfitting if complex models are trained using data sets of limited size, right? So remember that was the example where we had 9 points and we're fitting a 9-point polynomial through them, and yes, it fit every single point perfectly, but then when we sampled new points, then the predictions were really way off. Or conversely, we had a very simple model that didn't fit those points very well, but then it didn't kind of jiggle too much for a new data set. So how do we balance these two things? It says limiting the number of basis functions in order to avoid overfitting has the side effect of limiting the flexibility of the model to capture interesting and important trends in the data. Another way to think about this, kind of given the ideas that we talked about in the geometry of least squares, was remember that in that setting, our prediction was living in the span of the feature vectors, right? And so if we have fewer feature vectors, well, we're gonna cover less of the space, more or less, right? It'll be harder to come close to the data. So we don't necessarily want to reduce our features so much. Overfitting is a situation where you can essentially hit the target exactly. You essentially have so much flexibility that you can always hit the target exactly, but then the way you hit it is not hasn't captured the actual information in the signal. It's kind of just fit to the various wiggles in it. It's kind of, you overfit the wiggles in the data because your model, you have so many features that you can kind of fit anything that's in the data, including the noise. So then the idea is, well, why don't we just reduce the number of features we have? It's like, well, okay, you can do that, but then that means that you might not be able to capture some of the interesting things you're after. So how do you kind of balance these two things? Okay, so although the introduction of regularization terms can control overfitting for models with many parameters, this raises the question of how to determine suitable value for the regularization coefficients, or how are we going to know how much to regularize? Now, seeking the solution that minimizes the regularized error function with respect to both weight vector and the regularized coefficient is clearly not the right approach, since this leads to an unregularized solution with lambda equals 0. So what he's saying here is, and let me zoom in a bit to show you guys. What he's talking about here is that if you've got you've got your I don't know, your target minus y of xw, whatever your squared, so that's your kind of goodness of fit term, and then you've got some regularization term. Let's say we were going to try to keep w small, and now you're going to say, well, you might think, well, why don't I just try to minimize this expression with respect to both the weights and this regularization term? Like if this is the thing that I'm after, why not just minimize with respect to both? Well, the problem is that, well, let's look at what the minimum value of this could be, right? The minimum value of this could be, this is a positive term, this is a positive term, so the minimum value could be, well, non-negative, so the minimum value will be 0, right? And if we have a complex model, well, we can achieve 0 here by setting the weights, there'll often be like lots of combination of weights that will allow you to exactly fit your targets. So this is kind of what we're talking about. A complex model can exactly fit the targets. So that term goes to 0. Okay, great. And now, well, we might have a penalty that, we'll have some crazy combination of weights. We'll have some penalty that's trying to keep those weights small, but if we set lambda to 0, if we're optimized with respect to lambda as well, we can set this thing to 0, and this regularization contribution becomes 0, right? So essentially it says if we optimize with respect to both for a complicated model, the answer will be get rid of your regularization and just fit the data exactly. So that's kind of not very, that naive approach is not very useful. So we have to kind of come up with something else. Okay. So it says, as we've seen in an earlier chapter, the phenomenon of overfitting is really an unfortunate property of maximum likelihood. So the point here is that we're picking kind of one answer, and we're not kind of taking account the kind of the flexibility of the model. And as we'll see in subsequent chapters, kind of the Bayesian approach does is allows you to kind of integrate, kind of marginalize out over the set of parameters that could be responsible for the data you're seeing. And when you have complicated models, there's more space to marginalize over. So that kind of implicitly kind of penalizes those models, as we'll see. So it says in this chapter, not this section, we shall consider the Bayesian view of model complexity in some depth. Before doing so, however, it's instructive to consider a frequentist point of view of the model complexity issue known as the bias-variance trade-off. So we're going to talk about this in the context of linear basis function models, but and I think the cool thing about it is that I think the insights from it, you'll hear these terms all around, so it's very useful to know what people are talking about. B, I think the insights are quite useful. Just what happens, what is it about simple models that maybe makes them too simple, and what about complex models? How do we kind of talk about that? So yeah, we'll see. Okay, so now we have to kind of think back to our decision theory time. So when we discussed decision theory for regression problems, we considered various loss functions, each of which leads to a corresponding optimal prediction once we're given the conditional distribution P of Tx. Okay, so remember the idea there was in that setting, so we're given this kind of P of Tx, and now in decision theory, the question was, well, okay, so what are we gonna, we want to report one number, one value based on the targets. What should we, with distribution of the targets, what should we report? And so let's call that I don't know, like h of x. Yeah, that's what we're going to call it in a second. So let's do that. And so the point was, well, to determine h of x, you say, well, you have to pick how you penalize being wrong, right? So there was kind of this notion of the loss function that was a function of your, well, let's just actually start with, the target and your estimate, your decision for the target. And so what you wanted to do was you wanted to pick, let's say, an h of x, which would be equal kind of to the minimum over h of x's over h as a function of the data, integrated over the target and then also the data, right? And so the whole thing hinged on how do you penalize, how are losses going to be measured? Is it going to be the absolute value of the difference, a squared difference? Like, do you have to get it exactly right? And if you don't, and we found that in different settings, different solutions minimize this loss. And a particularly kind of useful case, kind of mathematically easy case to consider, is the one where we're using kind of the squared loss. So this was just measuring things by that, and we found that kind of if that is our solution, if that's kind of the loss that we're going to use, then our optimal thing, which is called h of x below, is actually to report the conditional mean. Okay, so there are other solutions where our loss was different, but for the squared loss, and again, and we're going to talk about, we're just going to point this out in a second. This is just about how you penalize or how you evaluate deviations from this true answer when you want to make a decision. So this kind of decision theory loss, and this is completely different, unrelated to now how we're going to then try to achieve this decision. So this is just telling you, okay, well, if squared loss is the thing you care about, then what you have to report the conditional mean, And now then we have a second problem of, okay, well, now how do we actually, given our feature vectors, how do we achieve, how do we report that mean? And then that you can solve in lots of ways. But we've solved it in the past using least squares, but the point is that these are different things. So let's just, just keep that in mind. We'll talk about this in a second. Okay. The output prediction is given by the conditional expectation, which we denote by h of x, and which is given by this. So if you're using a squared loss, you want to report the conditional mean. At this point, it's worth distinguishing between the squared loss functions arising from decision theory, which was kind of this, and the sum of squares error function that arose in maximal likelihood estimation of model parameters. So just kind of saying these are kind of just completely different, different things. We might use more sophisticated techniques than least squares, for example, regularization or a fully Bayesian approach to determine the conditional distribution P of Tx. I'm not quite sure what he's meaning here because I think we're given P of T given x. I think maybe he's saying that, Bayesian approach, you kind of just keep P of T of x, you kind of report the whole thing. Yeah, not quite sure what he's saying there, but I mean, I think some of the points that are related to what he's saying is, well, okay, so let's say you've got h of, your h star of x, and now you want to, you want to kind of report, now you want to produce that h star of x. Well, you might choose to do that, using, and then minimize this with respect to w, using kind of, again, least squares. But you could do other things, right? Like you could maybe, maybe you want to minimize the 1 norm or whatever else. And so these are kind of just different aspects, and they can kind of be combined. So you can use this, this squared loss to the squared loss here from decision theory, tell you what you need to report, and then use a different loss to now show you how you can report that. So this kind of this is like, maybe we should call this this is the what, and this is kind of like the how. Now for what's going to come now, we're going to use the squared, this squared, least squares for both, but you can do other things. So I think that's what he's on about in this bit. But yeah, certainly worth distinguishing between the squared loss function arising from decision theory, which has nothing to do with our weights, parameters, whatever, and the sum of squares error function that arose in maximum likelihood estimation of the model parameters. Okay, so now, yeah, so we showed back in this section that the expected squared loss can be written in this form. So this was, remember this expected squared loss was, it was, the expected loss was going to equal to, the thing that we report minus t squared, average over all t's and x's. And the idea is you can just kind of, if you introduce a add and subtract an h of x is kind of the thing that you want to be reporting, then you can actually get this very useful expression in the case of squared loss, right? And now what are these two terms? Well, let's start with the second term. The second term is independent of y of x, so we don't have control over that term, arises from the intrinsic noise on the data and represents the minimum achievable value of the expected loss, right? So the point here is that, look, we have, both of these are positive numbers, so, well, non-negative numbers, so the best we can do is make things 0, but we only have control over this one. So if we set this to 0, we'll still have this to deal with. So that's kind of out of our control. It's just kind of the intrinsic noise in the signal. And so that's kind of the minimum bar. So we just need to work with this part. The first term depends on our choice for the function y of x, and we will seek a solution for y of x, which makes this term a minimum, right? Because it is non-negative, the smallest that we can hope to make this term is 0. So, if we had an unlimited supply of data and unlimited computational resources, we could, in principle, find the regression function. So if you have tons of data, you just figure out what it is to any desired degree of accuracy, and this would represent the optimal choice for y of x. However, in practice, we only have a data set containing a finite number of data points, right? In real life, we can't actually figure out what h of x is exactly, and so consequently, we don't know the regression function exactly. Okay, so again, he's going to touch on, okay, what would be the Bayesian way of doing this, and we're going to talk about it in I think the next section. But okay, so if we model h of x using a parametric function y of xw governed by a parameter vector w, then from a Bayesian perspective, the uncertainty in our model is expressed through a posterior distribution over w. Okay, but that's not what we're going to do now. So we're going to do the frequentist treatment. And it's a little bit, yeah, it's different. Okay, so involves making a point estimate of W, so what we've been doing, just reporting one value of W based on the dataset D, and then tries instead to interpret the uncertainty of this estimate through the following thought experiments. And notice that, like, in the frequentist approach, you have to kind of do all these thought experiments, whereas the Bayesian approach, things just kind of essentially just follow from the laws of probability. So that's kind of one of the advantages, I think, the cognitive advantages of the Bayesian approach. But nevertheless, it is always good to see things from different perspectives. So let's continue. Try following. Okay, so suppose we had a large number of data sets, each of size n, and each was drawn independently from the distribution P of t of x. So for any given data set, like the one we have, D, we can run our learning algorithm and obtain a prediction function y of x, and now based on D. Now different data sets from the ensemble will give different functions and consequently different values of the squared loss. The performance of a particular learning algorithm is then assessed by taking the average over the ensemble of data sets. Okay, so the idea is just to say, okay, well, yeah, we're just going to repeat this procedure over and over again for the different data sets and just take, compute our performance on each and then average over all the data sets. And this is going to kind of give us an interesting interpretation of kind of what happens and kind of our model complexity. Okay, consider the integrand of the first term of 3.37, which is this guy. This is the one we can do anything about, which for a particular data set D takes the form this thing. Now, because this quantity will be dependent on the particular data set D, we take its average over the ensemble of data sets. Okay, so if we add and subtract the quantity, of the expectation. So notice what is this thing? This is going to be for a single x value for which the optimal h of x is fixed. This doesn't depend on data set, because the optimal h of x depends on this distribution, whereas y of x depends on the actual instance of the data we've observed. So we add and subtract the quantity e of d, so the expectation, inside the braces, and then expand, we obtain, okay, so let's just kind of look at what he's doing. So we were subtracting y of x given d, we're subtracting h of x, so the value we're after, that decision theory told us to report, from the value that we actually are reporting based on this data set. So now we've added and subtracted the mean value of this across data sets. And now we just expand. So now we have this term over here, which is this thing squared. And then we have another term, which is this thing squared. And then we have finally a third term, which is kind of the cross terms, right? And so we now take the expectation of this expression with respect to D. Okay, so this is all indexed by D. You see all these D's floating around. And now we're going to take average things with respect to D. And the final term will vanish. And yeah, and the reason why it will vanish is this, right? It's actually really easy to see. So this thing has an expectation with respect to D. So it's just a number. So to take an expectation again does nothing to it. This same thing there. This doesn't even depend on D. And so if we take an expectation of this with respect to D, it becomes that term, right? So this gets canceled. So if you just take the expectation, let's see, if we take the expectation with respect to D, it goes to 0. And that, this whole term. So let me just be more precise. So this will go to the expectation of D of y, x, D, and then you're subtracting, and so that goes to 0. And then this whole thing will go to 0. So what we just shown is that the expectation over data sets, and you have to be careful with this stuff. Like I remember, I think when I first computed these things, many years ago, you get kind of a bit confused, and because there's an expectation, we're going to see in a sec, over x, so the actual data points for a given data set. But now there's an expectation over data sets, and that's kind of a key aspect, that we're actually taking these expectations over data sets. Like right now, for example, we've just been considering a single data point, x, and we just talking purely about expectations over data sets, and we see that, at that single point, the expectation of between our prediction, with the signal, what we're reporting, and the true value, now composed of the sum of these two terms, what's called the squared bias and the variance. Okay, so let's just see what he says about that. So we see that the expected square difference between y of xt and the regression function h of x can be expressed as the sum of two terms. The first term, called the squared bias, represents the extent to which the average prediction over all data sets differs from the desired regression function. So this is kind of a like in statistics, like the bias of an estimator, if I remember this correctly, is the expectation over its true value of, right? So that's kind of that's kind of what we have. We've got this expectation over the expectation over the data. So this is kind of the expectation over the standing in for the expectation of true parameters of our estimator. So this is kind of y of x versus the value that we're trying to achieve. So that's kind of the bias term. But the thing is, it's being squared, so it's kind of the bias squared. And now this is just a variance, right? Because you've got some random variable, which is a function of d in this case, and now we're just subtracting its mean over as a function of d, and just squaring it. So that's just that's like a normal variance, right? You have a random variable minus its mean squared. It's a variance. And the interesting thing is, what do these terms actually mean, right? So as he says, the first term represents the extent to which the average prediction over all data sets differs from the desired regression function. So it's talking about the average behavior, right? So if this is your function, and let's say we're just considering this point, and now you've got this crazy thing that's kind of doing all sorts of wobbles, it can still have very low bias because on average all these wobbles will cancel out, and on average you will get the exact value you're after. So that's kind of that's the bias term. And in very complicated models, I think the intuition for it is that models that are very complicated will tend to swing equally often above as below because they have so much flexibility. So on average, their bias will be low. They'll tend to they'll hit the thing, but they won't tend to be on one side or the other. They will because they're so complicated, because they have they can kind of swing wildly in either direction. They will tend to hang out on either side equally often, and your bias will be zero. But the second part, so you're like, oh, that's great. But the second part is actually now mentioning that variability. So it's saying, okay, given your expected value, how much are you swinging around that expected value? So now you can see these complicated models. Yes, their average might be very good, but there's lots of variability around that average. And so that's kind of the trade, the decomposition, right? That's happening, which is you're saying, well, how much bias is there? So how often on average are you hitting what the value you want? But then how much are you swinging around that average? And that's the variance. So it represents the extent to which the average prediction over all data sets differ from the desired regression function. That was the bias. The second term, called the variance, measures the extent to which the solutions for individual data sets vary around their average. So again, the cool thing is we've been talking about a single point, and we've just been looking at the effects of different data sets coming from the same distribution on our estimate. And so if the estimate is quite too flexible, let's say, for the data that we have, kind of like that polynomial, well, you can imagine that polynomial is going to swing wildly for different data sets around at a given point. Whereas a simpler polynomial wouldn't. As the extent to which the function is sensitive to the particular choice of data set. So that was the variance term. We shall provide some intuition to support these definitions shortly when we consider a simple example. Okay, great. So we're going to see this kind of happening in action. Now, so far, this is kind of important. We've considered a single value of x, and I like how he's built this up because there's kind of two kind of averages happening. So it's good to do them kind of one at a time, focus on a single point, and then expand out to all the points. If we substitute this expression back into 3.37, which was this one, we obtain the following decomposition of the expected squared loss. So expected loss is bias squared plus variance plus the noise. And the bias squared, notice now we've got the bias at each point now being averaged across all the data. The variance, the same thing, and the noise is kind of what it was before. And the bias and variance now refer to integrated quantities. So let's highlight that. Okay, good. Cool. Okay, so yeah, a lot of stuff going on here. Okay, so our goal is to minimize the expected loss, which we have decomposed into a sum of a squared bias, a variance, and a constant noise term. As we shall see, there is a trade-off between bias and variance, with very flexible models having low bias and high variance, right? Think of that polynomial swinging around, and relatively rigid models having high bias and low variance. So kind of a linear model, maybe it can't get every single data point correctly, it'll just tend to be below or above or whatever it is, but it's not going to swing around too much because it just doesn't have much flexibility. So I think this is kind of an important insight. The model with optimal predictive capacity is the one that leads to the best balance between bias and variance. Okay, and so yeah, so I think kind of one point that comes up is like I think let me grab one of these books here. Okay, so kind of a signal processing book, and there's a whole section in here on getting like minimum variance unbiased estimators and things like this, right? And I mean, I think the mathematics of it is beautiful, and it's nice to be able to work it out. But I think the point of this section is that you don't necessarily if you want to minimize your squared error, you don't necessarily care about unbiased estimators, right? Because maybe actually what you want is you want to introduce a little bit of bias, and the variance will come down so much that your kind of least squares solution, your squared loss will actually be smaller, so your actual performance will be better. So if you might heard these kind of minimum variance, unbiased estimators. I mean, why not have, why not reduce the bias if you can? But if your goal is least square, just the overall performance, you want there's actually a trade-off that's happening that you need to. So you might actually want to introduce a bit of bias. So that your overall, the drop in variance will be so much that your overall least squares or loss will be your overall squared loss will actually be minimized. So yeah, so just something to keep in mind. I've seen these unbiased estimator theory a lot, and I think the math of it is really nice, but not necessarily always the thing you want to do. Okay, so the optimal, there we go, and this is essentially what he's saying here. The optimal predictive capacity is capability is the one that leads to the best balance between bias and variance. Cool. Okay, so now we're just going to talk about this cool example, which I'm also going to reproduce in qualitatively reproduce in the code. But essentially, what he's done is he's there's that sinusoidal data. So let's have a look. So we generate 100 data sets, each containing 25 data points, independently from the sinusoidal curve h of x is sine 2 pi x. Looks like this. Data sets are indexed whatever. We're for 100 data sets, and for each data set, we'll just look at this picture in a second. Fit a model with 24 Gaussian basis functions by minimizing the regularized error function 3.27 to give a prediction function as shown in 3.5. Okay, so let's have a look. Yeah, so you guys probably can't see this super well, but the idea is data is coming from this. We're not going to draw the actual data points, and now we're going to be kind of generating fits for different values of regularization. And the point of all of this is he's trying to show kind of the bias and the variance. So he's saying that the bias is kind of effectively going to be the difference between this is the mean across kind of data sets. So you have these are the results for each of the these are the results for each data set, and then you can kind of compute the means at each point to get the mean across the data sets. And now you can this kind of becomes a measure of your bias. And kind of how wiggly these plots are becomes a measure of your variance. And now, as you can see, at high regularization, the plot, the fits are all well behaved, but you have actually quite a bit of bias. Whereas as you reduce the regularization, it starts getting very, very small. And you start getting all this kind of crazy wiggling stuff happening. All this wiggling behavior. So variance is going up, but now your bias is kind of essentially zero. So just kind of showing the dependence of the bias and variance on the model complexity. Okay. Yeah. So the top row corresponds to a large value of the regularization coefficient that gives low variance because the red curves in the left plot look similar, but high bias because the two curves in the right plot are very different. So that's what we just said. And then the opposite as we go down. Note that the result of averaging, so again, point about advantage of Bayesian approaches. The result of averaging many solutions for the complexity, for the complex model is a very good fit to the regression function, which suggests that averaging may be a beneficial procedure. And so actually in the Bayesian approach, that is what we do. We do a weighted average, but we actually, the averaging was with respect to the posterior distribution on the parameters, not with respect to multiple data sets. So there's always just one data set, and we just have uncertainty over our parameters, and we just kind of integrate over that to produce our estimate in kind of a, kind of a very reasoned way. There's no notion of like, okay, like having like different data sets and, averaging things like that. Right. Okay, so we can also examine the bias variance trade-off quantitatively for this example. So I'm going to compute a few of these, and we'll compute them ourselves as well. So the average prediction is estimated from this thing, which is just your average over the different data sets. And then you just compute the bias term. So remember, this is the average at each point minus the true value. We're just going, instead of integrating, we'll just average over a bunch of points on the line. And the variance is the same thing. So notice what we have here. We have like the y for a given data set minus the prediction, the mean prediction over data sets at that point. So that's kind of this thing. And then now averaged over all of the points. So that's kind of like, this is kind of our approximation of this term and that term. Okay, very good. These quantities along with their sum are plotted as a function of log regularization. We see that small values of, well, let's just have a look first. Okay, so here it is. We'll reproduce this plot too. So again, regularization here, and now we've got this average. We've got the errors averaged over data sets and points. So what are things to notice? So as we go this way, regularization is increasing. So notice that the bias is increasing, right? At low regularization, there was no bias. As we increase the regularization, we stop, we start moving away from those, nth order polynomials to like more simple models, for example. So as we increase regularization, the bias is increasing, but the variance is decreasing. And the bias squared plus the variance is this term. And the test error is, on held out data has a very similar shape, but kind of shifted. So it's kind of like, so the minimum value of bias squared plus variance occurs around here, which is close to that value that gives the minimum error on the test data. So kind of if we minimized, in this case, at least we minimize kind of the sum of the bias and the variance, then we would kind of find the parameter that, gives the best kind of test error, which is kind of what we expect, because we built this by averaging over kind of data sets. So, it's not surprising that the best value is showing up again at the same place it would on held out data. Okay, so let's see what he says. These quantities, along with their sums of bias and variance, are plotted as a function of ln. We see that small values allow the model to become finely tuned to the noise on each individual data set, leading to large variance. Conversely, a large value of lambda pulls the weight parameters towards 0, leading to large bias. Okay, so now although the bias-variance decomposition may provide some interesting insights into model complexity issue from a frequentist perspective, the limited practical value, and the reason why is that because the bias-variance decomposition is based on averages with respect to ensembles of data sets. So like, the point is, whereas in practice we have only a single observed data set. And if we had a large number of data sets, we'd be better off combining them to a single large training set, which then would fix the, which will at least, address the overfitting issue, because now we have more data to fit our parameters to. So now we're going to kind of contrast this approach to the Bayesian approach, which will kind of take care of some of these kind of conceptual issues and kind of in a very, and practical issues in kind of a very natural way. Okay, so I think that's basically all there is in this section. So I think it's just important, even despite the the frequentist Bayesian thing, I think it's just useful to think. At least I found it useful to think about in terms of kind of bias and variance. But again, it's kind of the simple idea that the simpler models will tend to have more bias because they can't fit every single data point. But because they're so simple, they also can't kind of wiggle around too much. Whereas complex models are, on the other side, and kind of the optimal, at least in the squared error solution, is kind of somewhere in between. Good. Okay, so I think with that, I think it might be a good time to have a look at. Let's have a look at the code. So let's switch gears now. So the very first thing I wanted to show you is just, he's talking about his model with the 24 basis functions, what that looks like. So this kind of goes back to our last chapter, how to encode inputs into features. So here we have a single input, which is, our input x, and we're going to encode it into the activity of these 24 basis functions. So what does that look like? So I actually had, because Mathematica is still not very natural for me, I had ChatGPT write me some code. But again, here's kind of what it looks like. So we've got on the x-axis, oops, let me switch. So if we take that off, great, you can kind of see. Okay, perfect. Okay, so there we are. On the x-axis, we've got the value of the input, and on the y-axis is activation. And I've plotted kind of the tuning curves, kind of the regions where each of these these basis functions are active. And then I've also plotted their actual activations, kind of centered on each one of the Gaussians. So, for example, now I'm going to move the inputs around, and hopefully you can see that as we move around. So, for example, let's kind of focus on this particular activity. That's the activity of this particular basis function. And as we move x is this kind of dashed line. As we move x, you see that its activity goes up and down. And then once we're kind of very far out, then it's completely zero, and a new set of basis functions have going to come online. So essentially, the point is to show you that the encoding we're getting looks like 25 different numbers, and most of them, well, depending on how wide these tuning curves are, will be zero. But the ones, the few basis functions that are around the value that you're using, around the input value, they'll be active. And so that's kind of the input that's going into your prediction, basically. So you're gonna have to kind of find a weighted, a weighting of all of these responses to produce the the outputs you're after. Okay, so that was the just to show you kind of what it would mean to actually encode things with 24 Gaussian basis functions. And now, I've got this, so I just wrote this up for you guys, and so you should be able to. It's on GitHub. I'll give you the link so you can just download it. Let me zoom in a bit more. Yeah, so I'll just kind of quickly run through it in case you want to play around with it yourselves. So all we do is, in this bit, we just kind of generate the data sets, and the data sets are simple. So the x's will typically just be equally spaced from 0 to 1, and the true y values are just going to be the sinusoid. Well, not the true value. Sorry, our data set is going to be the true values, which is the sinusoid, plus some random noise with some standard deviation. And now to compute the features, we need to compute the activity of all of those Gaussians. So we do that here. We first have to figure out what the means of the Gaussians are. So we just, again, linearly space those out. And then we just compute the activations of each one of those Gaussians for the given input. And we also append, this x is a vector, so we also append kind of a ones feature, which is just to allow us to, I was called phi 0 before. It's kind of the bias term to allow us, different bias term, the constant offset term that allows us to kind of capture constant effects. And so here in the next bit, we look at a couple of our generated data sets. The orange. And notice all the inputs are all at the same. The x's are all the same values, but the y's will have different values because of the noise. This is, again, the feature activation. This is what I just showed you actually in Mathematica. So as we vary x, these features will kind of come on and off, and that's why you're kind of seeing their kind of Gaussian shapes. And there's kind of there's a constant feature at the top, which is just always on. Okay, so now we've got the code that actually solves, figures out, what W is, and you have to just go back to the previous section to figure out, to determine how to solve, how to produce W, but it was just, the phi, transpose phi, all that stuff. So that gives us both, so this function gives us both the weights and our estimate of, our prediction. So we just kind of plot, and so with this we can kind of plot already our version of his first figure, showing what happens as we reduce the regularization, kind of going up and going down. We can see the bias is decreasing, but the variance is increasing. So just like what he saw. And now we can kind of finally go and plot that bias variance decomposition plot. So we're going to do it with 100 data sets, but first let's just try, we're going to try computing some training error and test error on one of the data sets. So we compute the features for one of our training data sets, and the W, we compute the training error, so the difference between our prediction and the actual data squared. That's the mean squared error for the training error, and then do the same thing now on the test data. Look, we've learned these weights on the training data, so we don't recompute them. We just produce the predictions for the test data, and we compute that. And now we plot this. So here is here is what it looks like in the case of, if lambda is 1, and you can see, so we've got the data is in blue, the fit is in orange, and you're reporting the error here. And then on the test data, it's just 1,000 randomly selected points, and you can see kind of what it looks like. And you can see in this particular case, for example, the average error on the training error is less than the test error, as you might expect. Okay, and then so finally we're kind of in a position to compute this bias variance decomposition. So I just kind of did some of the derivations that we went through in the chapter already at the top. So that the expected difference over data sets between our prediction and the true value is equal to the variance plus the squared bias, which is what that is. Yeah. Good. Okay, so now we're just going to go and run through a bunch of regularization values and through each one of our data sets to build up the bias, the variance, the mean squared error, which should be the sum of the two, and then the training error and the test error. And so that's kind of what this next bit of code does. Again, for each one we just generate the true data. We compute the feature vectors that we need. We compute the weights, and we just add that to our list for a given data set. We compute the training error, so by subtracting y hat minus y train, the mean squared error. So that's going to be the difference between y hat and y true. So that was, remember, I think in the chapter it's called, the y true is just called h. And then we compute the test error as well. And then we just average, so we've been kind of adding up these contributions for every single, so we just for every single data set here. And so we just, in this step, we just average all of them across the data sets. Compute the average prediction across data sets that we need. So that's what we need to compute the bias. So that's what's happening here. And now finally we compute the variance by looking at the predictions that we're making. So that's the y hats across the different data sets minus their average across data sets. So again, that's just simply the variance. Pack these into arrays. Make sure that the mean squared error does actually equal to the sum of the bias and the variance, which is what we need. And then finally, just report the results. So here's what it looks like. We've got here's the bias squared. As the regularization is increasing, the bias is going up. In orange, we've got the variance going down. We've got the bias squared plus the variance, which is their sum. We've got the training error in red and the test error, which is above that. But you can see that roughly the place where we minimize the mean squared error, sum of the bias squared and the variance, it's going to be the same as basically the same, very similar location to where the test error is minimized, which is kind of the quantity we care about, the performance on left out data. So yeah, so I think hopefully that'll be useful for you guys to kind of see how these things are computed and play around with it yourselves if you're interested, see how it's all made. And yeah, I think that's it. That's it for this video. Hope you found this useful. Hope you learned something. Let me know if you did. Let me know if you didn't. Let me know if I made a mistake somewhere. Happy to change those. And yeah, looking forward to seeing you in the next one where we talk about the Bayesian approach to all of this. So hope to see you then.